Fluid power systems are everywhere in a whole variety of applications: automotive, materials handling and processing, medical and dental, aeronautics and aerospace, construction and mining, manufacturing and robotics, rail and marine, agriculture and forestry. Let's learn about this hidden giant, fluid power. Here we see pictures of the variety of applications of fluid power in amusement parks, automotive transmissions, excavation, vehicle testing, manufacturing. This diagram shows a hydraulic control system. Faster than a speeding bullet, almost. More powerful than a locomotive, most definitely. Able to leap tall buildings in a single bound, certainly possible. And unnoticed by the casual observer. Fluid power systems should have the Superman insignia inscribed on them. This pervasive hidden technology is based on a simple principle that leads people to think that implementation of fluid power is just a select, assemble, and run task. Nothing could be more untrue. At the end of the 19th century, in response to the need to transmit power more effectively from one point to another, hydraulic systems replaced traditional mechanical systems. During the Industrial Revolution, the development of fluid power was emphasized, but most applications were steady in nature and required only static considerations for design. At the beginning of the 20th century, hydraulic control system development experienced a major setback, followed by decades of stagnation, with the phenomenal growth of electric power. The stagnation ended as World War II drove the need for power transmission characterized by high effort and fast response, which only hydraulic systems could provide because of their superior power density compared to electrical devices. After World War II, the science behind the technology of transmitting power hydraulically was exposed by pioneering work at MIT. Over the next 40 years, it was industry, as opposed to the university, that became the steward of technology for the fluid power world. However, due to the evolution of mechatronics over the last 30 years, there is a resurgence of interest in fluid power control systems at universities, and industry-university collaboration is growing. Unfortunately, fluid power is often considered a specialist subject. Is electric power a specialist subject? In applications where large forces or torques are required with a fast response time and high accuracy, hydraulic control systems are essential. They have a more competitive power-to-weight ratio than electrically actuated systems, which are limited by magnetic saturation, and they excel in environmentally difficult applications. In addition, the hydraulic medium is mechanically stiffer than the electromagnetic medium. Self-lubrication and inherent heat transfer are also advantages. Fluid power applications are numerous. For example, vehicle steering and braking, and suspension systems, industrial mechanical manipulators and robots, and actuators for aircraft and marine vessels, just to name a few. They are all multidisciplinary systems and require a systems approach to design and implement. Engineering background required includes fluid mechanics, electromechanics, system dynamics, computer control systems, and electronics, a mechatronics background. The block diagram shows a basic hydraulic control system. Note the power conversions that occur throughout the system. The hydraulic fluid is pressurized by a pump, driven by a variable speed motor. The pressure of the fluid is regulated and stabilized by a relief valve and an accumulator, not shown in the diagram. A servo valve, driven by an electric valve actuator, provides a controlled supply of fluid into the actuator, either a piston cylinder device or a hydraulic motor, controlling both flow rate and pressure. Low pressure fluid from the servo valve is filtered and returned to the reservoir. A feedback digital control system completes the system. Today, the competitive advantage of fluid power is greatest in mobile applications. For example, mobile heavy equipment, human assist devices, mobile human scale equipment, and hydraulic hybrid passenger vehicles, where fluid power can be a compact, efficient, and effective source of energy transmission. The opportunities are great for the mechatronics engineer in this re-emerging field. Let's consider the advantages, disadvantages, and challenges of fluid power. Fluid power is the transmission of forces and motions using a confined, pressurized fluid. In hydraulic fluid power systems, the fluid is oil, or less commonly, water. In pneumatic fluid power systems, the fluid is air. Fluid power system advantages include high power density. Fluid power is ideal for high speed, high force, high power applications. Compared to all other actuation technologies, including electric motors, which are limited by magnetic saturation, fluid power is unsurpassed for force and power density. Responsiveness and bandwidth of operation. Fluid power systems have a higher bandwidth than electric motors and can be used in applications that require fast starts and stops and reversals, or that require high-frequency oscillations. Next, high accuracy and precision. Oil has a high bulk modulus. Hydraulic systems can be accurately and precisely controlled. Advances in pneumatic components and control theory have opened up new opportunities for pneumatic control applications. Heat dissipation and lubrication ensures reliability. The fluid circulating to and from an actuator removes heat generated by the actuator doing work, and also lubricates moving parts of the components. Heat is the predominant damaging mechanism in electric and electronic systems, and electromechanical actuators and motors have limited ability to dissipate heat generated. Compactness, lightweight, and flexibility. Fluid-powered cylinders and motors are relatively small and lightweight. Flexible hoses allow compact packaging. Stiffness. Hydraulic drives are stiff with respect to load disturbances. Stiffness is the slope of the speed, torque, or force curve. Control gains required in a high-power hydraulic control system would be significantly less than the gains required in a comparable electromagnetic control system. There are disadvantages to fluid power systems. Electric power is more readily available, cleaner and quieter, and easier to transmit. Hydraulic systems require pumps. There's oil leakage, flammability, and fluid contamination. Fluid cavitation and entrained air are issues. There is challenging physics, which leads to more difficult modeling and control. Fluid power system challenges include increased efficiency, compact energy storage and compact power sources, noise, vibration, leakage, safety, and ease of use. And lastly, create portable, untethered, human-scale applications. To begin our study of fluid power systems, let's first introduce hydraulics. Pascal's law. Pressure applied on a confined fluid is transmitted undiminished in all directions, acts with equal force on equal areas, and at right angles to them. As an example, consider this bottle filled with liquid, which is essentially not compressible. A 10-pound force is applied to the stopper with a surface area of 1 square inch. This results in 10 pounds of force on every square inch of surface area in the container. If the bottom has an area of 20 square inches, and each square inch is pushed on by 10 pounds of force, then the entire bottom of the container receives 200 pounds push. Here, Pascal's principle is applied to the hydraulic press and hydraulic jack. Here, an input force of 10 pounds on a 1 square inch area. This develops a pressure of 10 pounds per square inch, psi, throughout the container. This pressure will support a 100-pound weight if this is a 10 square inch piston. The forces are proportional to the piston areas, 10 pounds per square inch, 100 pounds over 10 square inches. Conservation of energy applied to the hydraulic press. Conservation of energy says the net work done on the system plus the net heat transferred into the system equals the change in the total energy of the system. Here, moving the small piston 10 inches displaces 10 cubic inches of liquid. 10 cubic inches of liquid will move the larger piston only 1 inch. The energy transfer equals 10 pounds times 10 inches or 100 inch-pounds. The energy transfer here is also 100 inch-pounds. 1 inch times 100 pounds equals 100 inch-pounds. Hydraulic power transmission. The source of power is an electric motor or an engine. The input is the pump, either a vane, gear, or piston pump. The output is the actuator, either linear or rotary. The pump pushes the hydraulic fluid into the lines. The lines carry the fluid to actuators, which are pushed internally to produce a mechanical output, which moves the load. Some actuators operate in a straight line. They are linear actuators. They are called rams or cylinders. They are used to lift weight, exert force, clamp, and so forth. Rotary actuators or motors give the system rotating output. They can be connected to pulleys, gears, rack and pinions, conveyors, and so forth. Let's consider variable speed operation. If the pump constantly delivers 10 gallons per minute and the cylinder volume is 10 gallons, the piston will move this far in 1 minute. This is maximum speed. If the pump delivers 10 gallons per minute, but a valve restricts the flow to 5 gallons per minute, the actuator receives only 5 gallons and only travels half as far in 1 minute. This is reduced speed. The excess 5 gallons per minute is diverted over the relief valve. The pressure relief valve protects the system from overload damage. When the load exceeds the valve setting, pump delivery is directed to the tank. The result is a definite limit to torque or force output. Reversible operation. In this position of the directional valve, the pump delivery is directed to the cap end of the cylinder. The piston extends. Exhaust oil is pushed out of the rod end and back into the tank. In another position, oil is directed to the rod end of the cylinder. The piston rod retracts. Exhaust oil from the cap end is directed to the tank. The relief valve protects the system by momentarily diverting flow to the tank during reversing, and when the piston is stalled or stops at the end of the stroke. Pressure in a column of fluid. Consider this 10-foot column of fluid. 1 cubic foot of oil weighs approximately 58 pounds. If this weight is divided equally over 144 square inches, the force on the bottom of each square inch is 0.4 pounds. Thus, the pressure at the bottom is 0.4 pounds per square inch. We see that here. Pressure is force per area. 58 pounds over 144 square inches is 0.4 psi. If the fluid column height is 10 feet, as we see here, then the pressure at the base of the column will be 4 psi. It is the height of the column, not its volume, that determines the pressure. Consider oil level above the pump and oil level below the pump. If the fluid level is 10 feet above the inlet of the pump, a charge or head pressure of 4 psi will be present at the pump inlet. If the pump is 10 feet above the fluid level, then the pump must create a vacuum equal to 4 psi just to push the fluid into the pump inlet. Atmospheric pressure charges the pump. The inlet of a pump normally is charged with oil by a difference in pressure between the reservoir and the pump inlet. It is necessary to have a partial vacuum or reduced pressure at the pump inlet to create flow. On the intake stroke, the pump piston moves out, expanding the pumping chamber. A partial vacuum or void is created. The atmospheric pressure pushes the fluid into the pumping chamber to fill the void. Fluid is pushed, not pulled, into a pump. Pressure differences push oil into a rotary pump as successive pumping chambers increase in size as they pass the inlet. Liquids vaporize in a vacuum. This puts gas bubbles in the oil. The bubbles are carried through the pump and collapse with considerable force when exposed to load pressure at the outlet. This will cause damage that will impair the pump operation and reduce its life. This is called cavitation. In addition, too low an inlet pressure permits air dissolved in the oil to be released. This oil-air mixture collapses when exposed to low pressure and causes the same cavitation damage. Driving the pump at too high a speed increases fluid velocity in the inlet line and, consequently, a lower pressure condition, further increasing the possibility of cavitation. The recommendation is about 12.2 psia at the pump inlet. Positive displacement pumps create flow. Pump output is constant, except for changes in efficiency, regardless of the pressure. Whatever goes into the pump is forced out. The sole purpose of a pump is to create flow. Pressure is caused by resistance to flow. Here the load is 8,000 pounds. The area is 10 square inches. The pressure equals the force divided by the area, which equals 8,000 pounds, divided by 10 square inches, which equals 800 psi. If 9.5 gallons per minute is lost through a leak, the oil must still move the piston. There is still a 8,000 pound load on the piston. The cylinder still moves, but at a lower rate of speed. The pressure is still 800 psi. Maintenance of pressure alone is no indicator of a pump's condition. It is necessary to measure flow at a given pressure to determine whether a pump is in good condition or bad condition. How is pressure created? Pressure is created when the flow of fluid is restricted. The resistance may come from a load on an actuator or a restriction or orifice in the piping. Here, when the faucet is wide open, all the pump flow passes unrestricted. There is virtually no pressure in the system at this time. We have 10 GPM flow. The restriction is not sufficient to limit the quantity of flow out of the faucet. It is still 10 GPM. Pressure in the system increases as the resistance to flow increases. If the restriction is increased further, the rate of flow will decrease until the faucet is fully closed, stopping all flow. Here we have 5 GPM going through the restriction. Pressure in the system increases until the relief valve prevents any further rise in pressure. The relief valve is set at 1,000 psi. The unused flow is diverted over the relief valve back to the reservoir. With the faucet completely closed, all 10 GPM will go through the relief valve at 1,000 psi. A relief valve should be used with a positive displacement pump. Parallel flow paths. Liquids always take the path of least resistance. When parallel flow paths offer different resistances, the pressure will increase only to the amount required to take the easier path. Here we see 3 parallel paths. Restrictions are 100 psi, 200 psi, 300 psi. The fluid can follow one of 3 paths. It will always take the path of least resistance. Here the fluid follows the path of least resistance through valve A because the spring in the valve offers the lowest resistance to flow. With the path through valve A blocked, as shown here, the path through valve B becomes the path of least resistance. The pressure in the system becomes 200 psi. When the pump outlet is directed to 2 actuators, the actuator which needs the lower pressure will be the first to move. Since it is difficult to balance loads exactly, cylinders which must move together are often connected to each other mechanically. Series flow path. Pressures are additive when resistance to flow is connected in series. The pressure at the pump is the sum of the pressures required to open individual valves. The pressure at this point is virtually zero. It takes 50 psi of hydraulic pressure here to overcome this valve spring. 50 psi of back pressure added to the 100 psi spring value of the valve forces the pressure to rise to 150 psi-G. 150 psi of back pressure added to the 150 psi spring value of the valve forces the pressure to rise to 300 psig. Pressure drop through an orifice. An orifice is a restricted passage in a hydraulic line or component used to control flow or create a pressure difference or pressure drop. For oil to flow through an orifice, there must be a pressure drop through the orifice. If there is no flow, there is no difference in pressure across the orifice. An increase in pressure drop across an orifice will always be accompanied by an increase in flow. Here, if the flow path is blocked through the orifice, the pressures will equalize and there will be no flow. The pressures are the same on either side as there is no flow. The pressure drop is zero. Note, the pressure drop is the difference in pressure between the gauges up and downstream of the restriction. It may also be expressed as delta P. If there is a flow path through the orifice, then a pressure drop will exist. This pressure drop, or delta P, is the force that pushes the fluid through the orifice. Here the pressure drop is 500 psi. If the pressure drop is reduced, the rate of flow will also be reduced. Force equals pressure times area. Here the relief valve is set at 2000 psi. This valve limits the maximum pressure in the system to 2000 psi. This controls the maximum force of the press. The force is 2000 psi times 20 square inches, which equals 40,000 pounds or 20 tons of pressing force. Here we see the fixed platen and the moving platen. And this is a hydraulic press. Speed of an actuator. How fast a piston travels or a motor rotates depends on its size and the rate of oil flow into it. Here we have a 1 GPM pump, gallon per minute. The 1 GPM pump will cause the cylinder piston to move 2 feet in 1 minute. This cylinder has a 2-foot stroke and can only hold 1 gallon of oil. So the speed is 2 feet in 1 minute. A 2 GPM pump will cause the cylinder piston to move 2 feet in 30 seconds. The rate of fluid delivery and its area determine the speed of the cylinder. The cylinder has a 2-foot stroke and holds 1 gallon of oil. So the force or torque of an actuator is directly proportional to pressure and independent of flow. The speed depends on the amount of fluid flow without regard to pressure. Velocity in pipes. Fluid velocity is inversely proportional to pipe cross-sectional area. The friction of a liquid flowing through a pipe is proportional to the velocity if the flow is laminar, that is, smooth. Should the flow become turbulent, friction varies as the square of the velocity. Here we see laminar flow, a transition, and turbulent flow. If the area is in square inches and the velocity is in feet per second, the flow rate can be measured in gallons per minute, where a gallon is 231 cubic inches. So velocity times area equals Q in GPM times this conversion factor. Work and power. Work is done whenever a force is exerted through a distance. Work equals force times distance. Power is the rate of doing work, or work divided by time. A horsepower is 33,000 foot-pounds force per minute, which equals 550 foot-pounds force per second, which equals 746 watts, and a watt is a Newton meter per second. Power P equals flow rate Q times pressure P. And the pressure in horsepower equals the flow in GPM times the pressure P in PSI times this conversion factor. The horsepower required to drive a pump will be higher since the system is not 100% efficient. Let's design a simple hydraulic system. We have a load 8,000 pounds. We want to raise 30 inches. To raise an 8,000 pound load 30 inches, a cylinder with at least a 30-inch stroke, as shown here, is required. If the piston area is 10 square inches, the pressure required to lift the load equals the load divided by the piston area, or 800 psi. The relief valve protects the system from overpressure by diverting the pump flow to the tank when the maximum pressure setting is reached. In this position of the directional valve, pump delivery is directed to the cap end of the cylinder. The piston rod extends, and exhaust oil is pushed out of the rod end and back into the tank. The rate at which the load must travel will determine the pump size. Extending the rod 30 inches will require 300 inches cubed of fluid. If the total travel should take 3 seconds, a flow rate of 100 inches cubed per second is required, or 26 gallons per minute. If the maximum pressure is 1,000 psi and the pump efficiency is 83%, then an 18.2 horsepower pump is required. More on pressure. Pressure results whenever there is a resistance to fluid flow or to a force which attempts to make fluid flow, as from a mechanical pump or gravity. Here we see a column of fluid, 10 feet. A foot square section of water 10 feet high contains 10 cubic feet of water. If each cubic foot weighs 62.4 pounds, then the total weight is 624 pounds. This weight is divided over 144 square inches. This gives us a pressure of 4.33 psi at the bottom of the 10-foot column of water. Pressure head comes from the weight of the fluid. The pressure at any depth is always the same and is due to the weight of the fluid above it. A head of 1 foot, 0.3 meters, of water is equivalent to 0.433 psi, which is 0.03 bar or 9 kilopascals. A head of oil is equivalent to about 0.4 psi per foot, or 0.09 bar, or 9 kilopascals per meter. Atmospheric pressure and the mercury barometer. At sea level, atmospheric pressure due to the weight of air is 14.7 psia, pounds per square inch absolute. At higher altitudes, this pressure is less. Below sea level, it is more. Here we see atmospheric pressure here, and the atmospheric pressure supports a column of mercury this high, 29.92 inches. Pressure less than atmospheric pressure is called a partial vacuum. Let's look at pressure and vacuum measurement scales. First, gauge pressure. Atmospheric pressure is 0 psig. A perfect vacuum is minus 14.7 psig. A perfect vacuum is 0 psia, pounds per square inch absolute. Atmospheric pressure is 14.7 pounds per square inch absolute. Let's look at the mercury pressure scale. In terms of absolute, we have atmospheric pressure is 29.92 inches of mercury absolute. A vacuum is 0 inches of mercury absolute. While at atmospheric pressure is 0 inches of mercury, and a perfect vacuum minus 29.92 inches of mercury. How is flow measured? Flow is the action in the hydraulic system that gives the actuator its motion. Pressure gives the actuator its force, but flow is essential to cause motion. Flow is created by a pump. Flow rate is a measure of the volume of fluid passing a point in a given time. Velocity is distance per unit time. Here we see a constant flow rate, but varying velocity. The flow rate is constant in all sections. In the first section, the pressure we see is some value, and the fluid has some velocity. Here, the flow rate is the same, the velocity is less, the pressure increases. In the third section, the flow rate is the same, the velocity has increased, and the pressure has decreased, is the same as what it was back in section 1. Convenient conversion is that 1 gallon per minute equals 231 inches cubed per minute. Flow and pressure drop. Whenever a liquid is flowing, there must be a condition of unbalanced force to cause motion. Fluid flowing in a constant diameter pipe must overcome friction, and hence there is a pressure drop. Here, pressure is maximum at this point due to the depth of the fluid column. Friction in the pipe causes the pressure to drop from a maximum value to 0. The succeedingly lower fluid levels in these pipes is a measure of pressure at the points downstream from the source. And we see the lower pressure levels as we move from the source to the exit, where pressure is 0 because the fluid is unrestricted at this point. Fluid seeks a level or levels depending on the pressure. Here we see a pipe. The liquid is subject to atmospheric pressure at all points. The level of the fluid is the same at all points. Here, if the pressure is increased, then the liquid is still subject to atmospheric pressure at all points. The fluid is higher, but still the same level at all points. Note that in a hydraulic circuit design, the pressure required to move the oil mass and to overcome friction must be added to the pressure needed to move the load. Laminar and turbulent flow. Low velocity flow in a straight pipe is streamlined or laminar. This is the most desirable flow condition. Gradual changes in cross-section do not upset laminar flow. Gradual changes in direction do not upset the flow pattern. This helps keep pressure drops low. Laminar flow is in parallel paths and friction is minimized. Turbulence results in flow resistance. Friction is greatly increased. Heat is generated. Operating pressure increases, and power is wasted. Flow in a straight pipe is streamlined. Abrupt changes in cross-section upset the laminar flow and cause it to become turbulent. This increases the pressure drop and causes heating of the fluid. Abrupt changes in direction increase pressure drop due to the fluid flow becoming turbulent. This is highly undesirable due to heat and energy loss. Bernoulli's principle. Hydraulic fluid in a working system contains energy in two forms: kinetic energy by virtue of the fluid's weight and velocity, and potential energy in the form of pressure. Swiss scientist Daniel Bernoulli demonstrated that in a system with constant flow rate, energy is transformed from one to the other each time the pipe cross-section size changes. Bernoulli's principle says that if the flow rate is constant, the sums of the kinetic energy and pressure energy at various points in a system must be constant. Therefore, if the kinetic energy decreases, it results in an increase in the pressure energy. Similarly, if the kinetic energy increases, it results in a decrease in the pressure energy. The sum of pressure and kinetic energy is constant with a constant flow rate. In the small section of pipe, velocity is maximum and pressure is 300 psi. When the fluid reaches the large section of pipe, velocity of the fluid decreases and the pressure goes up. As the fluid leaves the larger section, it speeds up and the pressure drops back down to 300 psi. The Venturi effect in a gasoline engine carburetor is an application of Bernoulli's principle. Here, volume of air is determined by the butterfly valve. At the Venturi throat, the air speeds up and the pressure drops. The pressure is higher in the fuel bowl than in the Venturi throat. This pressure difference pushes the fuel into the moving airstream. Friction and velocity affect pressure. Friction reduces the head at succeeding points. However, when the pipe diameter is increased, the velocity of the fluid slows. This reduces the pressure drop, allowing pressure to rise in the larger section of pipe. Here are our most common hydraulic symbols. First of all, let's identify three lines. A working line carries main stream of flow. A pilot line, or sensing line, carries fluid used for control. A drain line carries leakage oil to a reservoir. Here is the pump inlet. It's a working line, so it is a solid line. Here is the return lines, which are working lines, and they are also solid lines. The pressure line is a working line, so it is a solid line. The pilot lines operate valves or other controls. They are long dash lines. They operate with low flows only. Short dash lines are drain lines. They drain leakage oil from pumps, valves, and motors. Rotating components: a pump, a bidirectional pump, a motor, a bidirectional motor. The fluid energy triangle points out, showing the pump as a source of flow. Two fluid energy triangles show the pump to be bidirectional, meaning direction of flow may switch between ports. The triangle pointing in shows the motor receiving energy. Two triangles show the motor to be bidirectional. The motor is reversible. Cylinders. This is a single acting cylinder. Here is the piston rod, and one port connection. A double acting cylinder has the piston rod, but two port connections. Here we see three pictures of valves. First is a relief valve. We see the in port, the out port, the flow path. We see an adjustable spring, and we see a pilot line. This is a directional valve. The three boxes means the valve has three positions, 1, 2, 3. The arrows show flow paths and direction of flow. Port connections are drawn in the centered or neutral position. Pressure, tank, cylinder A, cylinder B. This is a directional valve that is proportional. The springs are to center the valve on either side. The horizontal bars at the top and bottom show an ability to be infinitely positional, as in servo or proportional valves, where the directional valve in B is a bang-bang type of valve, and it's not positionable. It is either in one position or another. It cannot be positioned as the servo valve can be positioned. Lastly, here is an entire hydraulic circuit with a reservoir tank, a pump, relief valve, directional valve, motor. And we see they are connected to the reservoir. Here the reservoir is vented versus pressurized, which would be indicated by a closed top. And the lines are terminating below the fluid level in the tank versus above the fluid level in the tank. This concludes the introduction to hydraulics. To introduce the basic elements of fluid flow, resistance, capacitance, inertia, let's consider a fluid pipe flow example. So consider the flow of fluid in a constant area, rigid-walled conduit, which we see here. I break up the pipe into discrete regions of length L. Within a region, pressure and velocity are uniform throughout the region. Pressure and velocity may change with time, but space-wise within this region, they are constant. The same applies to other regions, n-1, n-2. These are lumps, and this is called a lumped parameter approach. The variables of primary interest are average fluid pressure P and the volume flow rate Q. So we are assuming within a lump, pressure and velocity are the same throughout that lump. They vary between lumps and they may change with time, but within a lump, they are space-wise uniform. The average flow velocity, V, is defined as Q, the volume flow rate, divided by A, the area, where A is the conduit cross-sectional area. The product of pressure and volume flow rate is fluid power, just as mechanical power is force times velocity, and electrical power is voltage times current. While the actual fluid pressure and velocity vary from point to point over the flow cross-section in a real fluid flow, we assume a so-called one-dimensional flow model in which the velocity and pressure are uniform over the area. Thus, average velocity and average pressure correspond numerically with the values at any point in the cross-section. These averages are space-wise averages, not time-wise averages. In a lump parameter dynamic analysis, the pipeline is broken into segments. Within each segment or lump, the pressure and velocity may vary arbitrarily with time, but are assumed uniform over the volume of the lump. By considering the behavior of one typical lump, we are led to definitions of all three basic fluid elements: resistance, capacitance, inertia. Experiments show that when a fluid is forced through a pipe at a constant flow rate, a pressure difference related to that flow rate must be exerted to maintain the flow. It is observed that it takes a larger pressure difference to cause a larger flow rate. In general, the relation between pressure drop and flow rate is nonlinear. However, some situations give a nearly linear effect. The pure and ideal fluid friction or fluid resistance element is defined as the difference in pressure between 2 points divided by the volume flow rate. Pure means the resistance only has the attribute for which it is named, resistance. Ideal means linear. For nonlinear fluid resistances, we can define linearized values about some operating point. Now consider conservation of mass applied to the nth lump over an infinitesimal time interval, dt. Conservation of mass says that mass flow rate in to this lump minus mass flow rate out of the lump must equal the time rate of change of the mass within the lump. During the time interval dt, the difference between the mass flow into and out of the lump must be equal to the additional mass stored in the lump. Mass enters the lump from the left at a rate of area times the velocity of the n minus first lump times fluid density, and leaves at the right at a rate of area times the velocity of the nth lump times the fluid density. Again, where rho is the fluid mass density, which we treat as being constant, corresponding to a constant operating point pressure and temperature. So for constant density, conservation of mass is the same as conservation of volume. So we have area times velocity, which is a volume flow rate. So area times velocity of the n minus first lump, which is the flow rate in, minus the flow rate out, which is area times the velocity of the nth lump, times dt equals the change in volume of that lump. And that can be expressed as volume divided by bulk modulus times the change in pressure of the nth lump. The bulk modulus is defined as change in pressure divided by change in volume per unit volume. It is a measure of fluid compressibility. It is a fluid property. The volume is the cross-sectional area times the length of the lump. Beta is the bulk modulus. dPn is the change in pressure of the nth lump. I replace area times velocity by Q, volume flow rate. Volume flow rate of the n minus first lump minus volume flow rate of the nth lump times dt equals area, cross-sectional area, times length divided by bulk modulus times the change in pressure of the nth lump. If I write this as an integral equation and solve for pressure, the pressure then equals the integral of Qn minus 1 minus Qn with respect to time times what I will call 1 over C sub F, fluid capacitance, where fluid capacitance is defined as cross-sectional area times length divided by bulk modulus. It's called fluid capacitance or fluid compliance. We can easily see the electric fluid analogy. Electric current is analogous to net volume flow rate. Pressure is analogous to voltage drop. And electrical capacitance is analogous to fluid capacitance. Newton's second law states that the force, which is pressure times area, the force difference between the left and right ends of a lump must equal the lump mass times its acceleration. Force equals mass times acceleration. For the nth lump, we have three forces: an area times a pressure at the left end, an area times a pressure at the right end, and then the force due to fluid friction, an area times the fluid resistance times the volume flow rate of the nth lump. And that equals the mass, which is density, mass per unit volume, times volume, area times length, times acceleration, which is the time derivative of the velocity. Area times velocity is volume flow rate, so this can be written as rho times L times the time rate of change of the volume flow rate of the nth lump. If I factor out the area, I have Pn minus 1 minus Pn minus the fluid resistance times the volume flow rate of the nth lump equals density times length divided by cross-sectional area times the time rate of change of the volume flow rate in the nth lump. Since this equation contains both resistance, friction, and inertance, another word for inertia, since it contains both of those effects, let's consider each in turn negligible to separate them. With zero fluid density, no mass, in other words, the right side of this equation would be zero, I see that the difference in pressure at the left and right ends equals the fluid resistance times the volume flow rate. That's my definition of fluid resistance, pure and ideal fluid resistance. If the resistance, the friction, were zero, we then have the change in pressure, Pn minus 1 equals rho L over A times the time rate of change of the volume flow rate. And I define rho L over A as fluid inertia or fluid inertance. Again, we see the electric fluid analogy. Pressure drop is analogous to voltage drop, volume flow rate analogous to current, fluid inertance analogous to electric inductance. We will return to the fluid compliance and inertance elements in more detail since they occur in more general contexts, not just pipelines. They were introduced here to illustrate that the three elements are always present whenever a body of fluid exists. Whether all three will be included in a specific system model depends on the application and the judgment of the modeler. Lastly, I include a table of ideal linear system elements for mechanical, electrical, fluid, and thermal systems. Let's focus on the electrical fluid analogy. An electrical capacitor, a fluid capacitor. An electrical inductor, a fluid inductor or inerter. An electrical resistor, and a fluid resistor. So we will be exploiting the analogies among these various disciplines throughout the entire course. That concludes our introduction to fluid power systems. Let's now move on to an introduction to thermal systems.